All right, so I'll kick it off with a brief introduction of the host for this event. I would like to, we are the volunteers from Career Voyager. This is the ML Journal Club event of the Career Voyager. We are affiliated with an organization called ZGZG Events. If you want to know more about the organization, you can see the WeChat HR code on the left-hand side. And for our Journal Club event, we have a Discord server, which is a QR code on the right. So feel free to take a screenshot and scan them, or just reach out to me whenever you are. If you're in the call, and I see everyone in the room already, we're already on the Discord server, so we're probably good. So today we have 2 papers to go through. Let me stop sharing. The 2 papers are, one second, stop streaming. Okay, today we got Ran to talk to us about 2 papers. One is the CHAMP, which is Controllable and Consistent Human Image Animation, and the other is called Animate Anyone. I think it's also about multimodal guided animation or video generation. So without further ado, thank you, Ran, for going through this paper with us. Please go ahead and start talking.
Okay. Yeah, so basically I will rearrange the order. So when I told Sean the order should be champ, then animate one, but now when I make the slides, I realize that animate anyone is kind of more foundation method. So we start from animate anyone and extend to what champ did in the paper. So let me introduce myself. I'm currently working for Tencent America, and I'm doing research in AI and filmmaking process. So basically, we want to do kind of intelligent video generation and a kind of controllable 3D generation and video generation. So today I will talk about so I called it multimodal guided generation. So basically, if you hear about this sentence, so maybe you think about what GPT-4o and what Chameleon and what Gemini did. But what I gonna focus today is mainly on video generation or on this different model. So let's think about what is multimodal, this term. So basically, it refers to, for example, different media type. For example, image, video, voice. For example, the audio, and probably also the text. And this is what the other large model what it's doing. So for example, the GPT-4o could take different modality input. For example, the audio, the image, the text together, and also output different modality.
One
Yep.
thing from my manager.
Sorry.
Someone talking?
Okay, so I just continue. So here I want to mention that in today's talk actually, we want to stress that the multimodal data is not just only the audio, video, image, and text, but different kind of image or different kind of video could be another model, another modality. So let's start from what the paper is about. So basically, I'm gonna talk about the motion guided video generation. This is a very more focused or more detailed topic of today's paper. So let's see a few demo of the 2 papers. The left one will be the Animate Anyone, the right one is the champ. So you see, so all the video here is generated by the model. So this is generated by Animate Anyone, and on the left it's on the right it's generated by champ. So basically, the topic, the task is how to generate realistic human motion video. For example, if you think about Sora, so basically there are a few examples that showing the human motion video in what Sora posted at the very beginning. For example, the Tokyo scenario, the woman that walking on the street of Tokyo. But we would realize that even Sora, I mean Sora is maybe the best video generation model. In their example, there still be we call it the non-physical motion of the human motion. For example, if you see the woman on the street, actually, in some of the frames, you realize the legs are kind of crossing, so it's not kind of the realistic motion of a real human. So this happens because Sora is a kind of generic model. It's trained on millions or billions video clips, but they don't have a very concrete representation of human or of a certain entity. So that's why if you just tell Sora that generate a human working, so in the embedded space in the latent space, actually maybe it's goes to another direction slightly, and you will see some artifacts. In these two papers, Animate 21 and Champ, actually they tackle the problem from another view. So think about we only care about the human motion. So for example, if we see the different animation, different film, actually there's a very special process in filmmaking, in the filmmaking pipeline, which is called mocap. It's so the term is motion capture. So basically, the motion capture is you actually in front of the green screen, the actor is kind of making different motion and try to try to reflect what the film is talking about. So based on this kind of shooted footage, you using some different algorithms, you can extract the skeleton motion of the actor. And then you can, in the traditional filmmaking pipeline, you kind of retarget the skeleton motion of the actor to another virtual actor. For example, most of the Disney and Pixar animation is kind of based on these mocap techniques. So inside this process, the key data or the key representation is skeleton motion, and this is one of the key modality these two papers focus on. So let's see what's the problem that these two papers try to really solve. So here shows some examples. So basically, the input of Animate 21 and Champ is two different things. So the first one is an image which reflects the human appearance. You can input any kind of image, your portrait photo, or even a generated human image. And the second one is we call the open pose modality, which is essentially the skeleton of the human, and it's kind of a video. So you see the skeleton of the human is actually moving, and on the right it's the result. So the thing is we have a moving skeleton, and how do we generate the video that have the same motion sequence but have the identity of the input image. So this thing is the problem that the Animate 21 and Champ paper try to solve. Yeah, so you can see that it's to my understanding and my feeling is it's pretty realistic. I mean, even it's very close to what you see in your real life. But all the video on the right is actually generated. There's no such motion for this identity.
Ren, can I ask a question?
Yeah.
for the pose sequence as input into both papers, we are already assuming that we have the process pose sequence either directly from motion capture of individual points, or it's already like.
Oh, sorry. Can you meet your computer? I didn't try.
You did.
Okay, go ahead. I think that there's echoes on link.
Okay, is that done?
Yeah.
Okay, cool.
Yeah,
I
no.
guess there's multiple people joining the room. Can you hear me now?
Yes.
Oh, sorry. No worries.
This is my fault.
No worries. So for the pose sequence that's input into both papers, are they already pre-processed pose sequence either directly from the motion capture with direct control points? We know where they are, or maybe it's a video but already processed. We're not talking about how to get a pose sequence from a video in these two papers, right?
Yeah, we're not talking about how to do the pre-process. So basically, this skeleton motion is either from mocap or you can extract it from any input video. So
Gotcha.
there's a bunch of different algorithms to generate the human motion skeleton from an input video, from monocular video. This is
Gotcha.
a pretty mature research direction.
I see. Thank you very much.
Okay, so then we have a feeling of what the problem is, and then let's ask ourselves, or just ask yourself, how do you solve this? So basically, I was thinking about this problem, I think 1 year ago, and I saw a few solutions from the community. For example, there are some artists try to solve a problem using ControlNet and Animate diff. So basically, I'm not sure if you are familiar with these two technology. So ControlNet is a kind of generative network that can generate image from input guidance. For example, the left image here, so you see the skeleton, and this would be the input of the ControlNet, and then ControlNet can generate the image in the middle and also in the right. But the thing is, the ControlNet only care about the kind of the input guidance, but there's no control of what actual appearance you generated. For example, the identity in the two images here are only controlled by the prompt. But the thing is, for the prompt, you don't have a very accurate spatial control. For example, you can say generate a girl that's wearing these blue pants, but you don't have more detailed control telling maybe in the middle of the pants should be green or red. That's very difficult problem in the prompt engineering. Yeah, and another thing.
Sorry, one more question. So ControlNet, the input is only the skeleton motion, or is that skeleton motion plus a static picture of the model?
Only the skeleton, only the skeleton image. So the ControlNet itself is just a guided image generation.
I see. Gotcha.
Yeah. So there's are two dimensions of the problem. So first thing is from ControlNet we have a very abstractive input like this the skeleton image, and the ControlNet, what ControlNet do is from the skeleton image to generate another generated image that have the same pose, but you have no control of the details of the generated appearance. You can control maybe a very rough appearance by prompt, but you cannot do specific spatial control. And another thing is the ControlNet is only generating images. So another dimension is we want to turn images into videos. So here we use another technique called Animate diff. So this is another paper from the same author of ControlNet. They are really doing very good in this domain. So Animate diff is maybe I think for now it's most widely used open source video generation framework, I think. So basically, it try to aggregate all the latent in the video. For example, for every frame, you have the go through the video. You have the latent of the image of every frame, and they try to concate all the frames into a kind of spatial temporal latent, and try to learn the motion from this spatial temporal latent. So finally, what Animate diff doing is it can kind of smooth the different image frames. For example, if you use ControlNet to generate the images for every frame in the video, actually you will see the flickering effect. For example, because every image is generated separately, and the prompt cannot have the very specific and very accurate control of the appearance. So you will see the different appearance in every frame. And what Animate diff is, it can smooth the appearance change and make it more like a real video. So we can see what happens here. Yeah. So basically, from left is a motion sequence, and in the middle and in the right are different styles of the generated video. So you can see if you stop and see every frame, it's good. It's very sharp, and the identity, also the appearance looks pretty real. But if you see it as a video, you see the close color changes and the identity changes, and you from the point of view of a realistic video, you will see, well, it looks cool, but it's not a good video, right? Yeah. So this solution is from the community, and would be the very intuitive solution if you don't want to train your specific model. Yeah. So the pros and cons of this solution is the pros is actually because you use the ControlNet, so the generated video actually follows the motion. So that's a good point. And another thing is if you stop, then you get a very good image. So every frame is a good image. But the cons, the bad part is first there's nearly no consistency. So you see the smooth change, but from the semantic view, actually there's no consistency. And another thing is there's the reference accuracy, because here there's no reference, so you don't respect to certain reference. And yeah. So here I should put this point into the pros. Another good point is it's very easy to implement because you don't need to train your own model and just use the inference code of ControlNet and Animate diff. You can generate the video. And so I mentioned that we thought about this problem last year,
Sorry.
and yeah.
Sorry for kind of a naive question. So ControlNet generates static images, and Animate diff makes the motion a little bit more consistent between different frames, such that it looks like an animation, but it's not consistent enough because of the identity and color. Is that the right understanding? Because Animate diff adds some consistency, right? Just not enough.
Yeah. So Animate diff actually focus on the motion. So they call it the motion module. So if you think about the motions in a video, so if every frame has the same identity, for example, it already has the consistency in identity and appearance. Then what Animate diff do is try to realize certain motion. For example, you move from left to left to right, then it can kind of generate the frames in between and also smooth the sequence. But there's a so what we saw here is actually, so if every frame has different identity, so it already have the flickering. What Animate diff is, it also kind of try to smooth the whole sequence, but the final result is what you see here. Yeah. So in general, it's a smooth video, but there's no consistency inside.
Consistency. Yep. Perfect. Thank you. Any questions from the floor? No? Okay, thanks.
Sorry, I have a question. So, in general, how do you evaluate the performance of the model? What kind of metrics do you use?
Yeah, so basically, from the image generation, there's a few basic benchmark. For example, there's this stochastic benchmark, and also there's human perception benchmark for the image generation. And for control net, there's a very direct metric we can do is because if you generate an image, you can extract the pose again and to see if the input pose and the output pose is close enough. But for video, for example, because control net and animate diff, they are kind of independent work. So there's no specific metric or benchmark that can test timing for the whole process, for the whole pipeline. But in video generation, I think the similar thing happens. I mean, for image generation, you have you have this semantics benchmark, like you generate image and you run the clip, you run clip again and get the text words from your video, and try to compare with your input text. But but for the guided video generation, I think the very specific thing you can do is also when you generate the video and you extract the pose again and compare to the input pose. And another thing is regarding the identity and the reference is for every image actually you can for example, the very naive way is you can compare the generated every frame, the generated image for every frame, you compare it to the reference image. So either in kind of the feature extraction way, or you can simply run kind of latent self-attention, and you get kind of the metric here. Yeah, but I think in all the papers I am presenting, I think there's no very specific and very effective metric for evaluating these things. So finally, what tells the final answer is the human feeling. So if you feel it's a kind of smooth video, or if you feel it's a real video, then it counts. So that's also another problem in the video generation field. Is most of the metric for now is not aligned with human feeling that well. Yeah, I'm not sure if this already answered your question.
Yeah, sure. This definitely. I mean, this seems very tough thing to really find out. For example, when you see the girl's jacket change color, whether you call it this is something creative and supposed to be that, or it's we trying to avoid, right? So
Yeah. That's the thing we are dealing with every day. So because we kind of shipping the similar solution to the film studios. So sometimes they want a consistent video, sometimes they just want a creativity. So so we cannot generate the both of these in at once, right? So we have to talk to them. Some of the model you get the smooth motion, you get the consistency. Some of the model you get maybe the flickering if you really want it, right? So yeah, so that's one of the kind of key problem in the video generation field.
Yeah, very nice. Thank you.
Yeah, so I mentioned that 1 year ago we were thinking about the same thing. So we also have our own solution. So here shows another demo. So you see here is the input. So the input is we made using Miko Dance software to generate a dancing video of the Genshin Impact character. And what we did is we trained another network called this neural texture network, so it can kind of transfer the style of the initial video to another style. So these things is not exactly what we want, because we want to have the animation for any input reference image, but in our solution we cannot animate arbitrary reference image, but more like you give me an initial reference image, for example, what we get from the Miku Miku dance, and we do a cell transfer, and then we for example here, this would be an initial reference image we got from the input video, and what we did is we transfer this image to another style. For example, here we have 3 different style, and then we use the method called neural texture to generate the consistent video for every style that have the same motion sequence.
Oh, sorry. What's the input for this model? We have the skeleton plus a complete video.
Yeah. So actually, this input should be just the complete video. So here, so the input MMD video. So
I see. So there is no skeleton over here.
Yeah, but there's something similar. So when you render this video, you have for example, we call this UV coordinate, which is another thing. It's not the skeleton video itself, but another guidance. So yeah, so in general, the 2 solutions are totally different direction, but finally it solves a pretty similar problem.
So basically, the consistency and continuity here is guaranteed by the source video. So you don't have to do anything to control it. You just need to make sure the new texture is consistent. Is that the way it is?
Yes, but the thing is, if you just run, for example, control net for every frame, you still have this flickering effect. So what we did is we use the guidance, for example, in this in this scenario, it's UV coordinate. We use UV coordinate to build we call the neural texture, which is you can think about the neural texture is when you see a video, so every pixel in every frame, actually they have kind of intrinsic consistency. For example, if you see the eyes, so in every frame, actually the eyes corresponding to the same object, like the eyeball, right? So actually the in every frame you can calculate the UV coordinate or kind of the guidance for the eyeball. So basically, if you just see the UV coordinate, for example, the eyeball is the coordinate maybe it's 10 and 10, right? So in every frame, you can you can try to retravel where is this point. So in the video, if you just extract the color of the eyeball, actually you get a curve. So it's only one-dimensional data. Of course it has a 3-channel RGB, right? So what we did is we try to train a neural network that try to smooth the color change of this one-dimensional curve. So the color change here is not.
So the input is the source video plus a semantic guidance, like a reference image, like style image or text. I'm just curious. So the input is just a video, and where is the target style? That was my curiosity.
Yeah. So input is a video, and kind of another modality is UV coordinate, which
UV
is
coordinate.
you can think about. Yeah, you can think about it's a kind of segmentation of the character. Yeah, but in the segmentation you have like from the top left it's 0, 0, the right down it's just the maybe 100, 100. So you have the segmentation, and in the inside the segmentation you have a kind of coordinate or a certain value for every pixel. So these are the two input modality, and another thing is the style. So still, you can also just input one of the image that you transferred from the initial image.
I know in rendering, we have UV, which is basically the texture we're going to wrap around a mesh. Is that the same UV you're talking about, or?
Yes, yes.
Oh, okay, gotcha. Thank you.
Yeah. So basically,
and the UV is static, right? The UV is static, or is it a movie of UV coordinates, or it's just a static UV mapping?
Actually, it's a video of UV coordinates.
Ah, gotcha. Thank you.
Yeah, so you can get the UV from either directly from your rendering engine, or you can run this optical flow calculation to get the UV directly from the video.
Yep.
So basically we solve the problem using still using control nets, and also we train a network to represent the neural texture. So basically the result is pretty consistent, very stable, and the image quality is also very good. So let's see what's the pros and cons of this solution. So basically the good point is it also follows the motion, and the image quality is I think it's very good. And also we have the consistency. But the problem is because it's used this kind of neural texture, and essentially it's kind of smooth the the difference from every frame. So finally, some of the details existing in the single image is not in the video anymore. So it's there is a kind of loss of the details. And another thing is the diversity, because the process I mentioned, so we need an input video and a kind of style transfer of the input video. So this kind of restricts the diversity of the generation. For example, you cannot really use another character follows the same motion of the input. And another thing is it's really difficult to scale because it's still kind of cascade solution. You need to calculate UV, you need to build the neural texture. So it doesn't scale in the kind of different inputs, and it also doesn't scale in the kind of the video dimension. So basically, we saw the different attempts, different solutions that the community provided and what I provided, right? So finally, we can figure out what we want. So there's a couple of things that is definitely needed in this topic. So the first thing is we need quality. For example, if you just pause the video, you see a very good image. And the second one is diversity. So you want to have the motion, but for different characters. So you don't want to only kind of animate someone. You want to animate anyone, right? And another thing, the very important thing is you need the consistency. Otherwise, it's just a different generated image sequence, but not a generated video. And regarding to the reference part, because we also want the diversity, but we still need every frame that respect to the same reference image. And another thing is, of course, we need to follow the human motion. And the final thing is, we want this model to be scalable. So either in the character, in the diversity, and also in consistency. For example, the long video consistency. So all of this is kind of solved by the paper I'm presenting today, the Animate Anyone and Champ. Then let's see how they solve this. So basically, here's the overall neural network structure, the architecture for Animate Anyone. And probably you see a lot of things, but most of the architecture is identical to a normal diffusion model, for example, Stable Diffusion. So the main difference from the Stable Diffusion or widely used different model is 3 parts. So basically, the first one is the reference net, and the second one is along with that reference net, they use another term, a special term called the spatial attention. So and finally, there's another thing is called post guider. So the idea of these 3 parts are pretty simple, but all the techniques of these 3 parts is not existing in other papers. So that's the main novelty of this paper. Let's kind of dive into the 3 parts separately. So the first one is the reference net. So the reference net, so if we hear about the reference net, then we must kind of recall the concept of control net. So basically, for the control net, I mentioned in the very beginning that the control net, what control net generates is from an input modality, for example, the skeleton image. It generates another image that follows the same motion or the same skeleton image. But for reference net is we have another constraint. For example, the reference net itself is give a reference image. We can generate another image that have a very similar appearance to the reference image. So basically, if you think from the very high level, these things are quite similar, because when you think about control nets, so what we want is the input and output have the same skeleton image, the skeleton guidance, right? For the reference net, what we want is the input image and output image have the same guidance reference. So yeah, so basically, I think fundamentally these 2 networks are almost the same, very similar. Yeah, but we can still see the difference. So the first, there are a few key differences here. First thing is, so the blue line here is clip, so the text guidance. So it's very normal in almost all different models. So the text guidance is go inside and have the cross attention to both of the original different model and also the reference net. And there's are the same strategy that control net and reference net did in this scenario. Is for example, in control net, the left part is the original stable diffusion network, and in reference net, the lower one is the original stable diffusion network. So what they did is they copy the network to another instance. For example, in control net, the right one is at the very beginning, it's identical to the left different structure. And in reference net, we have the upper one and the lower one at the very beginning. They are the identical one. But the difference, yeah. So finally, what we want to train is we want to train the copied version of the different network, and kind of modify or optimize the weights inside the copied version, and keep the original version fixed, or they call it the freeze the original different model. So in reference net, it's the same thing that we want to train the reference net different model, and then kind of push it back to the original different model to make a difference.
Ren,
So
can I
the
ask 2
different,
naive
yeah.
questions? Sorry, 2 very naive questions. One is, what is a zero convolution?
Yeah. So basically, yeah, it's a very special trick in control net, and it also used in different papers. For example, also in reference net, they have a very similar concept. So the zero convolution is you can think about the processing in control net, right? So if you just delete the whole right part, then it's a stable diffusion itself, right? So for example, if you want to optimize all the weights in the new copied network, think about if you want to you can do the combination by simply add the latent or the feature map in your new network and the old network. For example, input ZT is just a latent feature map, and now you just add them up to your latent feature map in the copied network, and then so the control net is only trains on encoder part and only applies to the decoder part of the original stable diffusion. So what will happen is, if you have a different weights in the copied network, and if you just simply add them up, then you introduce the very different noise distribution back into the stable diffusion. So finally, you will see suddenly there's the semantics changes a lot in the generated image, and finally you got very blurred image and very bad result. So what zero convolution did is it introduced a kind of a convolution kernel with just one pixel, so 1 by 1 pixel, and the initialization of this convolution kernel is 0. So you have for example, the convolution kernel is just a Gaussian kernel. So you have the Gaussian parameters and also the offsets, they call the bias to be 0. So at the very beginning, if your input latent map and do a 0 convolution, finally you get nothing. And so at the very beginning of the training, you are only using your original stable diffusion to generate the image. So finally, in the first steps, you see the same image, but you don't see the change, but the image quality is still the same, the very good one. And then if you calculate the derivative over the convolution kernel parameters, actually you get the derivatives. So the thing here is start from the 0 convolution. You can optimize for the weights in the network and also the parameters of the convolution kernel. So finally, the result is it's slowly evolved to a better convolution kernel and also a better weights here.
I see. So 0 convolution, 0 means the initialization is all zeros.
Yes.
Is that just the bias, or also the kernel itself?
Also the kernel itself.
I see.
Yeah,
you mentioned a Gaussian. Did you mention a Gaussian kernel at some point?
Yes. So the zero convolution, the parameters is just the Gaussian kernel parameters. So the Gaussian is actually we have the energy of the Gaussian, right? And also the bias of the Gaussian. So basically, finally it learns two things. So one thing is how to deal with the condition. That's the weights in the network, and another thing is how to apply this network to the original network. That's zero initialized convolution depth here.
I see. Thank you.
Yes.
I have one more quick question. So in the reference net, we don't have a time dimension, but in the denoising UNet.
Actually, So because I thought about I mentioned about this is there are three different parts, right? So basically, the reference net and spatial attention only takes the image, only takes the spatial part. So here the reference net is essentially the very similar solution with control net. It also only generates the static image. So here you see the temporal attention. So the temporal attention in this original UNet is identical to Animate diff. So this is not the kind of novelty of this paper of Animate and one and Champ. So here the temporal attention is just a copy of Animate diff, and in the implementation is people just fine tune an Animate diff stable diffusion here. So the temporal attention here is not that important, but I will tackle this in postgraduate in another parts. Okay.
Gotcha.
So in these slides,
Jane, could you help mute yourself? I think you forgot to mute. Thanks.
Yeah, so in this slide, actually, we build the link between ControlNet and the ReferenceNet. Yeah, but the main difference is yeah, so basically the whole structure, the training strategy of ReferenceNet is almost the same with ControlNet, but how to apply it is very different. So in ControlNet, actually, you only train the encoder part, but only apply to the decoder part. And in ReferenceNet, actually, you apply to every layer, not only the UNet encoder, but also the decoder. So the reason is so actually in the paper they mentioned the difference here. So their intuition for this, I think currently there's no complete accurate answer for this, but their intuition is for ControlNet, the guidance, or for example the skeleton image, the guidance itself is spatially aligned with the input image. So that means whatever you did in the encoder part, actually they have the same kind of coordinates, the same local semantics to the input image. So you don't need to really influence the input image to make it kind of have the sense of your guidance, but only when you decoder, you see what the guidance did and add them up to your noise latent, and finally you get the aligned image. But in ReferenceNet, so we mentioned before that the ReferenceNet is not generating image from, for example, the skeleton image, but from a reference image. So you can think about you have a human in the first frame, but in every generate frame, the human has different pose. So spatially they are not aligned. So that's why we have this fully connection from every block, because we from the very beginning in the encoder part we need to take into account the reference one. So yeah, so this is the explanation in their paper, but I think theoretically it's not a perfect answer. I think maybe in the future we can have better understanding. Yeah,
I'm
so
sorry,
basically.
I'm so caught up by the previous question, if you don't mind. You mentioned zero convolutions is a 1-by-1 pixelized convolution, but then you also mentioned Gaussian. I thought Gaussian convolution means a spatial smoothing kernel, and if it's 1-by-1, I maybe it's a different kind of Gaussian. Can you help me understand?
Yeah, so actually I was not deeply into this stuff. So so for now I can only imagine. So for the details you can refer to the original paper. So what I
I see.
imagine is yeah. So what I imagine is for example at the very beginning it's just a 1-by-1 kernel, but when the optimization goes, it kind of try to see the adjacent ones.
I
So
see. I see.
finally,
Okay.
it's kind of Gaussian kernel, kind of optimized Gaussian kernel.
I see. I see. Thank you.
Yeah. So, yeah. So finally, the main difference between ReferenceNet and the ControlNet is the ReferenceNet you have the connections for every block. Yeah. And another thing is how to use the connections, because from the architecture level you only see that we have the blocks from so every layer from ReferenceNet we connect to the stable diffusion layers. Yeah, the next part is how to apply this connection. So basically, if you for the original stable diffusion, actually we only use this self attention, and also in ControlNet, because they are the two nets are basically trained separately. So there's also for the encoder part there's only the self attention, and for the decoder part it's just only the cross attention. But in ReferenceNet actually they have another special trick here is they call it the spatial attention. So basically you can think about the frames the frames of the video here. So every frame has the height and weight, and then you aggregate all the temporal parts. Then you get a kind of 3D matrix. So basically, this is a kind of volume. So this is a representation of the video. Of course, it's in the latent space. And the reference image is just an image. So you have this height and weight. So first you need to kind of concate them together. So how they do this is they copy the reference image to the length of the temporal part, and so it's just the h and the h by w by t, but for every slice in the temporal part, it's the same image, and then you get the same dimension of these two kind of latent maps, and you concate them together and calculate the self attention, and then only extract the first part for the dimension of the videos. So how this act is finally it's kind of calculating the influence of the reference image that applies onto the video frames, also in the latent maps. So if you use self attention, actually you get the same dimension, but the special attention they mention here is they only extract the first half of this representation. And then goes to this cross attention is so the cross attention input will be the clips, the text guidance, and the temporal attention is what they take from Animate diff that makes this temporal latent map more smooth in temporal domain. Yeah, so the reference net are basically these two parts. So the fully connected architecture and also the spatial attention blocks. And another thing, the final thing of this paper of Animate 91 is the post guider. So basically, I mentioned the yellow network here. I refer to this network as the original stable diffusion network, but if we say it correctly, it's not at least in Animate 91. So for this thing, we can refer to another paper that published before Animate 91. So Animate 91 is published by Alibaba. This Damo Yuan, and another paper called Magic Animate is from ByteDance. So the result of Magic, so the task of Magic Animate and Animate Anyone are almost the same. That input the image and the motion guidance, and then finally we generate video. But the video generated by Magic Animate is not as good as Animate Anyone. So we can call Animate Anyone maybe it's a GPT-3 point of human video generation, but Magic Animate we can say it's maybe just half of the impact. So, but if we look at the network structure of Magic Animate, that's what I mentioned before. It's a very naive, very plain structure. So we have in the middle the stable diffusion network, which is freezed everywhere, and in the lower part it's control net. So remember what control net is. It's try to train encoder but apply to decoder. So here it's just a control net takes the post guidance, and on the upper part it's the reference net. So this would be the initial version of the whole network. And in Animate Anyone, they found out the stable diffusion part, the original network, and the control net network is kind of redundant, because if you train this, you see that you copy the original one to control net, you also copy the original one to reference net. Finally, you got 3 times of the memory. So in Animate Anyone, they found out the control net and the original one are just redundant ones. So what they did is they just fine tune the original stable diffusion model and merge the the original one and the control net one into this this denoising unit. So so here, because they are not directly using control net, so you can you have to train your own input encoder, so not just only using control net. So they call this encoder is post getter. So so basically, what the post getter doing here is very simple. So the post getter is just a few convolution layers. So from the input image, you apply a few convolution layers. Essentially, it's just smoothing the image and kind of Gaussian blur the image. And what they do here is also another very simple operation. Is you just add this to a noise image. So think about what this is doing is pretty similar with what you do in image inpainting, in generative image inpainting. So in image inpainting, actually you keep the foreground the same and just apply the noise to the other parts. So here you have the post guider blurred and add it up to the noise image. So it's like doing painting from the poses. So yeah, so here is still a very simple trick. And yeah.
What's the data representation in post sequence? Is that RGB channels, or is every channel a different control points?
It's just RGB channel. So
Gotcha.
so that's a tricky part. So even though we say the human motion is another modality, how we deal with it is we just treat it as an image. So I think that's one of the key problems in current solutions, but surprisingly it works very well. So so here is basically we take the pose sequence as image sequence, as color image sequence, and just apply convolution layers and add to the noise. Then take this as input to the original Stable Diffusion pipeline, and try to apply the reference net using this spatial attention, and try to add the text guidance using cross attention, and also try to apply temporal attention, which used by Animate. So yeah, so this network is so they have kind of training strategy. So the first trained network is the reference net only on image generation, and then they try to fine tune the network lower here, just from an animative checkpoint. So finally, if you implement it, it's kind of very simple. So what you need to do is take Stable Diffusion, take the Stable Diffusion checkpoint and set it as the initial model for the reference net, and try to fine tune it to this reference net function, just using image pairs, and then try to fine tune the lower so this post getter and the network here, and the network here is just you fine tune from the animative checkpoint. So finally, the code you need to write for this project is not that many. So basically, the thing is how you understand these three parts and how you arrange them into the original network. Yeah. So here, so to here we explained the three main parts in Animate N1. So the reference net, the spatial attention, and the post getter. And everything else in this network is just almost the same with original Stable Diffusion, Animative, and control net. Yeah, then let's think. Yeah, let's think further along this direction. Yep.
Ren, thank you. So before we go to the champ paper, is there any questions about the animative?
Yeah, may I ask?
Yeah.
Did you already explain the post guiders It is like just a multi-layer network, or it's more than that?
You mean the original Animate Anyone paper or?
Yeah, Animate Anyone.
Yeah. So here is here you can just think about the post getter is just applying kind of Gaussian blur to the original image. So there's no special trick here.
Okay.
So it's not a very complicated network which is trained.
Okay, and the post guiders pass into the lower network as is this as a local condition?
And just as the input, for example, because the input of the different model is actually this latent noise, right? So post getter is just makes the input original image. For example, the original image is the post image is still have the same resolution with the reference image, the input image, right? But the latent noise is smaller because it's in the in the latent space. So the post getter is just kind of applying the convolution kernels that take the input post image and kind of remap it using this Gaussian blur remap to the dimension, the resolution of the latent noise image, and just add the map to the noise. So there's no, I mean, special tricks here.
Okay. Okay, thank you.
Okay.
Any other questions?
Yeah, I think we can somehow extend this to Champ because it's just one thing here. So yeah, and then we can have the questions together because Champ is not still nothing new comparing to Animate Anyone. Yeah. So if we think about the post guider, so currently we take the input image and using this convolution layer and adapt to the noise. And then we need to think about it. If it's the best guidance or the best guidance modality, and another thing is if we have different guidance modality, I mean, even for the same task, how do we deal with them? So so in Champ is actually I think it's also a very intuitive extension that because we would think the skeleton image is the information is not enough for the video motion, right? So if we want more, for example, what I mentioned, we did before using this neural texture is we also utilize the UV mapping. So for example, if we want to use UV mapping and also maybe depth, normal, and also the skeleton together, then we have maybe multiple channels of guidance. And this is what Champ did. So the network in Champ is the same with the Animate Anyone.
这样气泡音乐。
那个 audio 质量不好。
Sorry.
Let me let me try to mute. Sorry.
Okay. I will go ahead. So basically the overall architecture of the network is same with Animate Anyone and Champ. Also the author of Champ is also another researcher in Alibaba. So I think they share the fundamental ideas. So the reference net. So the only new part is if we have multi-channel guidance, what do we do? So basically, what they do is first they want to kind of makes the guidances more accurate. For example, if we only use skeletons, actually no matter how the identity or how the human shape is, actually they have the same skeleton. And if you learn based on the same skeleton, actually there will be variances in different training data. So finally, maybe you don't learn that well. So in Champ, what they did is they first do this called parametric shape alignment. that from the reference image, they try to fit a simple model. So a simple model is a parametric. Sorry. Sean,
Yes. What's happening?
so I still hear the voice from Rain, I think.
Oh, really? Oh, I muted him, but maybe I only muted for myself.
Yeah, I think so.
Yeah. Ryan, can you mute yourself if you don't mind?
Yeah. Let me see. Okay, I got it.
Thank you.
Yeah. Okay, let's continue. Now it works. So basically, what they did at the very beginning of this new post gather, right? So we for now we have we want to have multiple channels of guidance. So the problems for of the skeleton guidance is it does not fit for different I mean shape the body shapes. For example, if you are a bit fatter than the other ones, then the guidance maybe have misleading influence. So so basically, what they did is they try to fit a parametric body shape model, which is called simple. And this is widely used in both mocap, in computer graphics, and in animation. So this is a very mature research direction, and they just use the existing algorithms to fit the simple model to the input reference image. For example, the rest shape or the initial shape of the simple model is a bit slim, and then you get kind of grow it to the body shape of the input image. So for now, we have a better guidance, and for the better guidance, actually, we also have different channels. So when we have the simple model, we can render the depth of we can render the depth of the pose. We can render the normal of the pose, and we can also render the UV of the pose. So here is not only using skeleton motion, but we also add 3 different channels: the depth, normal, and UV back to the pose gather. So here the thing is you can still just simply apply for different guiders you different guidance using post guiders, but the thing is it's similar with control net. So if you take more guidance, then you need more memory, and the calculation is much slower. So what they did is they try to fuse the 4 channels back into kind of the single channel, and then adapt to the noise. So how they do this is they because the different guidance here, actually they are still different RGB image sequences. So the network does not really learn that very well with limited data. So how they do this is they first try to do a kind of they call this guidance self attention. So essentially what they do is they just calculate the self attention of each channel along the temporal domain, and then finally what you see is something showing here. So for example, the depth part, because the motion, the human moving actually has this intrinsic consistency. So if you just calculate the correlation of different frames, you have these peaks like the red parts for your for example for your body parts, and for your arm parts, because it moves more frequently, then you have less values. But these things, if you just calculate the self attention, you somehow highlight the information you need. And these things is also actually realized by a few other papers. There's another paper called Free Control or something, which is another strategy for doing control net. So here the using self attention to get this heat map is a kind of normal trick. So here we use this self attention and to get the heat map and just train another Fury network to make it to the kind of the the same dimension of the original post guider, and
Right.
then adapt to the noise image. Okay.
Right, two naive questions. One, for the 4 different blocks, are they just different attention heads, or are they have actually different neural net architecture?
So basically, if you apply this to the different, actually it's not the different attention heads. So what they want to do is because they don't want to use it as different attention heads or different noise input. So what they did is they try to merge 4 different channels into one channel.
I see. Thank you. The second question is a kind of naive one. I didn't follow. So for the simple model,
Yep.
what's the difference between the first column, second column, and third column, where they have 3 different copies?
So this one is just a different time step.
Oh, okay. Gotcha. Thank you.
Yeah. Okay. Yeah. So finally, what Champ did is just change the post guider to they call this kind of multi-channel input. But how they apply this is pretty similar, and just a few simple tricks. So finally, they showed a few better results than animated one, but because we are trying all the solutions recently to build up our own applications and our own solutions. So what we realize is probably these things does not work that well. I mean, comparing to Animate Anyone, the just the skeleton, there's not that much advantage for using different channels. So these things is just our feeling and what we test, and we got this feeling. I cannot guarantee if this is true, and I mean this situation happens for different neural network applications. So I don't have a very accurate answer if this is true, but I guess the skeleton guidance is pretty enough for this task. Yeah, and in the following part, I will show a few application we are working on and the result here. So one of the application is because I mentioned that I'm working on AI and filmmaking pipelines. So one of the applications we call the previous or another a more realistic use case is if you are a director or you are making a film. Actually, at the very beginning, you have to select certain actors, right? So normally you have to invite them to your office and ask them to do certain motion and see if it fits your expectation. But for now, using Animated One or using this post-guided video generation, you can say I only need one image of this actor, and you can generate any motion for this actor and see if it fits your expectation, fits your setup in the film. So you don't need to spend that many money that invite them here. Yeah. So that's one of the applications that we are pushing to the production level. Yeah. So you see, you can see that the result here, even you, yeah. So the best one is just 720p. So if you see it in a very high resolution, there's very little artifacts, and to me it looks very realistic. And yeah, here's another test we have, and so the input is just the image and post video, So finally, the generated video is very to me it looks very real. Yeah, so this is mainly the application we are working on, but still.
I have a just curious question for you. I'm not sure if you know the answer or if you're okay to share the answer. Do you think those papers are still kind of very research and they're just cherry picking a few good examples to show in the paper, or do you think they're actually pretty mature to be used and very robust?
So I think yeah, there's a different there are different levels of the results. So basically, actually we implemented Animate Anyone, and there's a few open source implementation. So basically, the results, if you just implement what they mentioned in the paper, or if you just use open source solution, the result is not as good as what they presented in the paper. So actually, it's totally different level. For example, the open source solution, I think is maybe only 60 or 70% of the quality of the result in their paper. So
Interesting.
actually, we tried different solutions, and finally we got, for example, this kind of quality, and also this kind of quality. So basically, there are a few factors. So one thing is also, of course, how you train your network. There's a few tricks inside. And another very important thing is how do you fill up the data. So basically, what we experienced is first you need to kind of train the network with a higher resolution, because in the original paper they trained the thing on the public data set. So actually inside the Animate Anyone, they are trained on a very special data set, which is not public one. And so that's why their result shown in the paper is very different from the open source implementation. So our experience in training this network is the different folds. So the first one is we need to kind of train it on a higher resolution. So using some techniques to feed the network into the GPU. There's a few tricks, but it's capable. So we can train maybe 720p, because original one is 500 by 500, but now we can train 720p 720p videos. And another thing is we need to select the data to kind of clean the data, because if you just kind of get data from maybe TikTok, from YouTube, from BiliBili, finally there's a lot of different artifacts in the video. For example, there's a lot of words, letters on the video, and it kind of pollute all the data set. And there's some visual effects in the video, which also is bad part of the data and will influence your final result. So I think the short answer for what Sean asked is, if you got very good data, and if you trained to the network to converge, for example, what we trained is about 16 cards for 1 week. So if the data is enough, then it's pretty robust. So all the results we show here, for example, this one, and this one. This one is not directly from our group, but from a neighbor group. It's not that cherry pick. So for example, I can say 80% success rate, I think.
I see. Thank you for the insight. Very valuable. Appreciated.
Okay, yeah, and but along this direction, we still not satisfied with that. For example, if you see the result here, comparing to another very secret work from another research group, for example here. So the quality comparing to this result is still I mean, there's still a very big gap. So yeah, so essentially they are using another method. So this method is very similar to what I mentioned, neural texture. But if we only care about the quality, this quality is, I think it's definitely outperform Animate Anyone or our current implementation. And another thing is the same group also do other works, like it's not only generating human motion video, but also other identity or other objects. For example, the animals. It can also generate very detailed motion, very detailed appearance, and that's our kind of future work. So the first one is to try to push the human motion generation to the limit, and another thing is apply this technique to other objects.
It's really interesting because for other animals, it's more difficult to find a robust parametric model, right? For human, we're all similar, but for different animals, there's no standard simple for them, right?
Yes, so that's a problem we need to solve. For example, one naive solution is you can kind of categorize the animals. For example, if you have dog, cats, and they have a pretty similar skeleton. And there's another paper. Yep. Go ahead.
Oh, I was gonna say, yeah, just categorize them into like with 2 legs, 4 legs, 8 legs, and then just do something like that.
Yeah, and another thing is, so basically we don't need.
Sorry, I don't hear anything. Is someone else talking? Ren, are you there? Is it us? Hello?
Hello, can you hear me?
Oh, yes, we can hear you now. I think you disappeared.
Okay. Yeah, my headphone just powered off. Yeah, I restarted. Okay. So basically, for different animals, we can use different pose. So there's a paper called pose anything or something that it accepts the different inputs, for example, animals and even objects. So this is one thing. And another thing is the accuracy of the skeleton, or I mean, both in position and in topology, is not that important. Because for example, in Animate Anyone, when you kind of pre-process the video to the poses, actually the poses, the quality, if you come from filmmaking industry, if you come from mocap process, or even if you come from like the post estimation industry, you see the result of the pre-processed open pose is not that good. So first, there are still some artifacts like the position arrows. It's very little, but it's not perfect. And another thing is the flickering of the open pose sequence. So it's not smooth. For example, if you have the mocap sequence, you will see it's a very smooth pose video sequence. But currently in the input of Animate Anyone or this kind of task, the input is not perfect. It's flickering. There's arrows there, and also there's maybe some parts, for example, your hand that disappears in some frame, appears in another frame. So that means the network itself is kind of already tackles this kind of not perfect data. So I think the power of large generative model is it kind of automatically deal with these corner cases. So I think for the answer of extending this to other objects, I think I think it's not that hard. You just find a kind of representation of other objects and train another network. I think it will work pretty well. Of course, there's something to polish, but it's not impossible. Yeah, and another thing is to just apply our current solution to yeah, to apply our current solution to more industrial level application. For example, what we can see is here. So if you already have a film footage, you wanna replace your actor with another one. So you can just extract the open pose of your actor and take another reference image, and finally you got yeah, kind of edited movie. Yeah, so I think that's all the things I want to talk about. And finally, I do a short summary. It's not about the techniques, but how do we understand the techniques. So I think Animate Anyone, Champ, and ControlNet and Animate, if everything here is pretty similar. So we can say there's nothing new. So basically, ReferenceNet is I think it's a kind of extended version of ControlNet, and Champ is just extended the post getter to multi-channel post getter. So yeah, in a word, it's nothing new.
Would you also
and
say
another
the
thing,
control? Would you also say ControlNet is an extension to Stable Diffusion? Latent diffusion.
yeah, so ControlNet is an extension to LoRa. So yeah, but I think what ControlNet introduced, for example, this zero convolution, and also this copy the Stable Diffusion to another copy and freeze the original one, optimized for the copied one. So this kind of architecture level stuff is pretty novel. So I think ControlNet is a very very good research. There's a lot of novelty inside. But for example, ReferenceNet is, I think it's still new and still very good research. but I think it's pretty similar with the original idea or the overall idea of ControlNet. And
I see.
Champ
So
is
basically,
just change a bit. Yeah.
so basically, it's worth probably investing to read into ControlNet if someone is interested.
Yes, sure. So yeah, so I think that's a thing inside most of the deep learning paper. So they share they share overall architecture, but adding a few small modification and tricks. Yeah, and finally I want to mention that even though we think it's kind of magic to animate anyone, right? But in the film industry or animation industry, there's another technique called rigging. So what you can do in the rigging is also you can control the shape by just applying different skeleton motion. Yeah, and here shows an example of Adobe Animator. So this thing is called rigging. So the rigging is just to control the shapes, control the video by using this kind of skeleton-like controllers. So these things, I think fundamentally they are solving the same problem, but in the context of rigging, what we solve is solving a numerical problem to calculate the heat map in barycentric coordinate. But the thing is, if we are using riggings, we need to kind of manually position some of the control points, and then apply using maybe a predefined motion sequence or something. But in Animate Anyone or this deep learning based method, we don't need that kind of manual work. But but another thing is how you don't need manual work when you do the inference, but you need manual work to collect the data. So I think finally it's a kind of solving the same problem using different ways. So the deep learning based method is using a data driven way, but the rigging is using a numeric way. So yeah, so I think finally there's no one that will dominate the task. So I think there will be someone using rigging, someone using Animate anyone, and which one to choose only depending on your final application. Yeah, I think that's all I have. So the take-home message is, you can think, you can kind of try to solve the traditional problem in a data-driven way, and if you solve it in a data-driven way, then just I mean, look at the existing network architecture and do some modification, then probably you get the result. Yeah. Yeah, that's all I have.
Thank you very much. Very extremely helpful, very valuable, and a lot of insights. Thank you so much, Ran. Is there any questions from the floor before we wrap up?
I I have some very naive questions. So, in the post night, like what is a post sequence? Does that include any like item that the person is interacting with, like he is like wheeling stored, something like that? Is that possible?
Yeah. So basically, in our current test, there's no object interaction, but there's interaction between your body and your clothes. So the thing is, currently all the training data or the definition of the problem is just animating kind of the human or animating the identity, but not animating the interaction. So I think our final goal is to really use this for film privatization or even generating a real film. So at that stage, we need the interaction between different human and the object, and also between the background and the object, or everything together, right? So, but currently, we think we need to solve it step by step. So for now, anyone solves the kind of human motion, and also part of the human and clothes interaction. And next task or next project we are working on is we try to animate objects, maybe not only animals, but also for example, if you have a ball, how the ball bounces on the floor, right? So this one is also can be solved by generative way.
I have a follow-up question. So, Ran, can you show the video for Animate Diff where the clothes are changing? Like the
You mean
clothes
Animate anyone, right?
Oh yeah. Sorry.
Okay. Yeah. So basically, this is our results. You can see the clothes. So the.
Oh no. I mean the early video where the clothes are changing colors, because I remember in that video there are some there's some background. Yeah. There are some background. I don't know. There are objects or.
Are they canny? Like art or?
All right. You see what I mean, right? On the left video, there are some structures in the back. Are those being used? They are, right?
In ControlNet, they are being used because it's just the edge modality. But
okay, gotcha.
yeah. So another insight here is we wanna if we compare this track of solution like Animate Anyone or something to Sora, right? So Sora actually learns. They call this world simulator. They learns everything in the world, or they learns everything in the video and synthesize a kind of realistic video. But finally, because they use end-to-end data-driven way, so finally there's no real physics inside. So our expectation is maybe at some point the data-driven way, the end-to-end data-driven way somehow approximate the physics. But if we think about along the Animate Anyone this track, actually the motion sequence itself is kind of physically plausible, because we can always apply, for example, the retargeting techniques in mocap to make the post sequence physical, right? So this is another way to kind of generate a physically plausible video. So that's another insight. So that's the way we are going.
Yep. Thank you. All right. Any other questions? If not, thank you so much, Zhang, for giving the amazing talk today.